Good morning everyone. I am Abhishek Singh. Today we will talk about intensifying screen. Principles. Fluorescence, the emission of light by a substance that has absorbed light or other electromagnetic radiation. In most cases, the emitted light has a longer wavelength and lower energy than the absorbed radiation. Therefore, it converts the X-ray beam into light. Intensifying screen are the part of the radiographic cassettes which is used to convert the energy of X-ray beam into visible. The visible light then interacts with radiographer films to form the latent image. Approx 30% of X-ray photons striking an IF screen will interact with the phosphor layer of the screen. They are absorbed by the phosphor crystals, which then becomes fluorescence. Example, emitting the visible light. Advantages of implanting IF screen. Patient dose decrease. It improves contrast. It saves the time of radiographer. Disadvantages of implanting IF screen. Slightly unsharpness that are blurring is caused. Reason for unsharpness: poor screen contrast, damaged cassettes resulting in damage to screen which produces screen artifact in the film. Greater the light diverge occur in the screen, the greater will be unsharpness. Rare earth elements. The rare earth elements describe those elements that have an atomic number between 57 to 71. These elements are traditional metals found in low abundance in nature. New phosphor developments from the rare earth series of elements is known as rare earth screen. The principal advantages of using rare earth elements: 2 times faster than conventional screen. Used become of high conversion efficiency. More efficient is comparison with gallium tungsten. Construction of intensifying screen. Number 1. Base. This layer is fastest from the film. It is made up of paper, cardboard, more of usually plastic such as polyester. Property A. Number 1. It should be chemically inert. Second, should be interact with the phosphor layer. Third, should be radiolucent. Fourth, should be flexible. Functions: provides strong, smooth, flexible support for the fluorescence layer. Second, substratum layer. It is binding or adhesive layer between the base of phosphor layer. It may be reflective or absorptive. First we will discuss about reflective layer. It is made up of magnesium oxide or titanium dioxide. Functions: it intercepts light emit in other direction and recreates into the films. Therefore, it increases the efficiency of IFS screen, nearly doubling the number of light photons researching the film. Disadvantages: it increases the unsharpness. Second, we will discuss absorptive layer. It is made by adding a color dye to it. An absorptive layer has an opposite effect to a reflecting layer. Any light backwards or towards the screen base is prevented from being reflected by the base or phosphor layer and is instead absorbed. Advantages: less unsharpness. Disadvantages: slower speed. Third, we will Phosphor layer, the active layer of the screen. It consists of fluorescent crystals which emit light when hit by X-ray radiation. Fluorescent crystal is suspended in a transparent binder such as polyurethane. The material effectively holds the fluorescent crystal together, and because many phosphor and hygroscopic, that is why the polyurethane is an ideal choice, because it prevents any moisture penetration which would otherwise cause film damage and reduce luminescence. In addition to the phosphor crystals, the binder in a high resolution screen may also contain carbon granules and or colored pigment known as acutants. Property: Phosphor should have a high atomic number so that the X-ray absorption is high. High convergence efficiency. Phosphorus afterglow should be minimum. Last layer, supercoat. This is the protective layer made up of acetate. It helps to resist surface abrasion and may also include anti-static qualities. The complete screen is attached to the front of the back of the cassettes by double face adhesive tape. It should be waterproof to protect the sensitive phosphor crystal. Screen speed. A screen is said to be fast when a small layer produces a given output of light and causes a certain degree of blackening of a film. The IF factor is defined as the ratio of exposure required to produce the same film densities with and without a screen. Therefore, the demonstrator is always less than the numerator. Then the IF factor of a pair of screen always works in unit. Conventional screens are available in 5 speeds in decreasing order. Number 1, ultra speed. IF factor is 200. Number 2, high speed. IF factor is 100. Number 3, medium. Par speed. IF factor is 50. Number 4, detail. Slope speed. IF factor is 35. Number 5, untail speed. IF factor is 15. Factor affecting screen speed. Intrinsic factor. Number 1, crystal size. Larger the crystal size, greater the speed. But due to the increases in light divergence, there is a loss of image sharpness. Number 2, nature of substratum layer. The presence of a reflective layer increases the screen speed but reduces the resolution. Number 3, phosphor composition. Well manufactured calcium tungsten efficiency converts X-ray into visible light, but rare earth phosphor are even more which is of no use or have a negative effect for intensification factor. Number 2, extrinsic factor. Temperature. As room temperature increases, screen speed decreases and film speed increases, so that no temperature correction is required for screen speed under ordinary conditions. Material used in phosphor layer, fluorescent layer. Infectional phosphorus, calcium tungstate, safe light, clumber color, activated by lead, color emitted blue, rare earth phosphor element, gadolinium oxysulfide, activated by terbium, colored emitted green. Second, lanthanum oxysulfide, acted by terbium, color emitted green. Yttrium oxysulfide, activated by terbium, colored emitted blue. Number fourth, yttrium tantalate, activated by niobium, colored emitted blue. Number fifth, lanthanum oxybromide, active by thulium, colored emitted blue. Name Abhishek Singh. Thank you.